Today we are going to be talking about the mole, which is one of the most important quantities in chemistry. So we're going to learn what the mole is, and then we're going to learn what we are going to be able to do with them, which is the more part of this presentation. The first thing we need to do is to understand what a mole actually means. And the best way to define the mole, in fact, the only way to define the mole, is to say that it is 6.02 times 10 to the 23rd particles of any given substance. So what do we mean by particles? Well, in chemistry, particles are usually atoms, molecules, or ions. This mole quantity, in other words, this number, is called Avogadro's number. And I really want you to remember that it's just that, a number. Whatever kind of atom or molecule or ion we're talking about, we have 6.02 times 10 to the 23rd of them in 1 mole. So here it is in all its glory, Avogadro's number. By the way, Avogadro was an Italian chemist who developed this mole quantity. In terms of our everyday experience, it might be a little easier to relate the mole to things like a dozen or a pair. Because a dozen, as we know, is just a number. If we have a dozen eggs, we have 12 eggs. If we have a pair of shoes, we have 2 shoes. It follows that if we had a mole of eggs, we would have 6.02 times 10 to the 23rd eggs, which would be a whole lot of eggs. We could make enough omelets to feed the world. Now, a mole in chemistry is what we really want to focus on. So let's think about the mole initially in terms of elements or atoms. So let's say we have a mole of oxygen. We would have 6.022 times 10 to the 23rd atoms of oxygen. Note that I just said 6.022. Sometimes you see the mole defined that way. Depends, different significant figures, but the basic idea is the same. So we could have a mole of oxygen, a mole of carbon, a mole of hydrogen, a mole of phosphorus. Things get a little bit more interesting when we start talking about moles of compounds. So let's say we have the diatomic molecule oxygen, or O2, or we have compound molecules such as carbon dioxide or water, H2O. So in this case, a mole is still the same thing. We have a mole of CO2, 6.02 times 10 to the 23rd molecules of CO2. Now that we have established what a mole is, you may be asking yourself, well, why does it exist? Why is it useful? Well, it's primarily useful so that we can measure masses. But in order to measure masses, we have to go back to the carbon atom before we address the mole. So a carbon atom is defined to be 12 atomic mass units, and this was actually somewhat arbitrarily decided by chemists working in the 19th century. Think of it this way. If we take this circle here, an imaginary carbon atom, and we divided it up into 12 units, each one of those units would be 1 AMU. And then, of course, by definition, 1 carbon atom is 12 AMU. This is very similar to a foot being 12 inches. Of course, this is a measure of length versus a measure of mass, but the principle is the same. Dividing a quantity, a thing, an entity up into 12 pieces. So the atomic mass unit scale was based on 1 atomic mass unit, which, as I said, is 1/12 of the mass of a carbon atom. Now, they had to choose among different isotopes of carbon atoms, and they used carbon-12. The good thing about this is that they then had a way to measure the masses of all the other elements on the periodic table based on this atomic mass unit. Now, in truth, if you looked up the mass of carbon on the periodic table, you would see 12.01. That's because there are different isotopes of carbon, and if you average them together in a sample of carbon, you will get 12.01. Now we can turn our attention to going from 1 atom and its mass to a mole of atoms. The molar mass is defined as the mass of 1 mole of a substance. If we're looking at silver, 1 atom of silver weighs 107.9 atomic mass units, while 1 mole of silver is actually 107.9 grams. This is very useful because when we look at the periodic table, we automatically get not only the mass of a single atom, we get also the mass of a mole of those atoms, and it's the same number with different units. This logic can be used for any element. Let's go back to carbon here. A single carbon atom, 12.01. A mole of carbon atoms, 12.01 grams per mole. This is useful. In order to give you a more physical sense of what goes on with these mole quantities, we can actually look at this picture on the bottom right here, and we can see what a mole of each of these different elements looks like. We see sulfur, which is this yellow powdery element, and we have a mole of it. A mole of it weighs 32.066 grams. We could go on down the line. Magnesium is a metal. It's solid. It weighs 24.305 grams. Tin, copper, silicon, different masses, what appear to be slightly different amounts, but in fact all equal 1 mole. You also might notice this is something we can actually work with in the lab. Can you imagine trying to work with a single atom in the lab? That would be pretty tricky, right? So here's where the mole really demonstrates its usefulness. This is stuff we can work with. We can weigh it out. We can use it. But remember, for any given element, we have the same number of atoms in that mole, but we have different mass amounts. We can move on now to calculating the molar mass of a compound. I'm going to start that out by just looking at an element and an atom of that element, which in this case is boron, so that we understand how to read the periodic table. Notice in this box in the upper right-hand side, you have one number that will give you the atomic mass, 10.811. You have to seek out that number when you are calculating the molar mass of a compound. So the mass of an atom of boron, I don't mean to beat a dead horse here, is 10.81 AMU, and the mass of a mole is 10.81 grams. Let's say, however, we want to calculate the mass of a mole of boron trichloride. Well, we have a guide to doing that here on the right. We're going to obtain the molar mass of each element from the periodic table. We're going to multiply the molar mass by the number of moles in the subscript of the formula, and then we're going to add our masses together and get the mass of our molecule. Now notice if we look at boron, the B doesn't really have a subscript, so that means it's just 1, and Cl has a subscript of 3, so that means we have 3 chlorines for every 1 boron. So let's go ahead and do this calculation. Our problem is calculating the molar mass of boron trichloride. We just established what the mass of boron is. Now we need the mass of chlorine. So again, we look at the periodic table and we figure out that chlorine is 35.45 grams per mole. Now let's think about the molecule and its actual structure. Notice that the blue center here would be boron, and then these lighter blue molecules that are bonded to boron are chlorine molecules. This means that there are 3 chlorine atoms for every 1 boron atom, and that there are 3 moles of chlorine for every 1 mole of boron in this molar quantity. Now, all we have to do is add this up using the appropriate subscripts. So 1 times our molar mass for boron plus 3 times her molar mass for chlorine, add the 2 together, and we get 117.17 grams per mole. Here's a practice problem. This is very similar. you need to calculate the molar mass of calcium chloride to the nearest 0.1 grams. A nod to our significant figures, right, which we need to keep in mind. Now, go ahead and do this, following exactly the strategy that we just followed. I will flip ahead so that you can see the answer, but best idea is to practice this on your own. There's our answer, 111.1 grams per mole. The next good thing and powerful thing that we can do with moles is we can convert from mass to moles and back again. We want to keep in mind that molar mass by definition is grams per mole. That's something we're going to refer to as a conversion factor going forward. And it's going to allow us to convert from mass to moles as seen here. We're given that we have 12.5 grams of salt, NaCl. If we multiply by the reciprocal of the molar mass, remember I said molar mass by definition is grams per moles. So we're going to flip this over and we're going to put moles on top and grams on the bottom. Why? So our units cancel and we get the correct answer for the number of moles of 0.214 mole NaCl in 12.5 grams of NaCl. Now we can do the reverse. We can go from moles to mass. In that case, we multiply the moles we're given, 0.122, by the molar mass as written, 58.5 grams NaCl per mole of NaCl, and we get 7.14 grams. Units must cancel. You have this molar mass, right? And you just have to decide whether moles need to be on top or grams need to be on top so that when you multiply out, your units cancel appropriately and you get to the unit you want for your answer, ensuring that your numerical quantity will be correct. Now you can again practice with this problem, grams to moles. Helium is kind of a cool gas, so I thought I'd just mention a few things about it. One thing I learned recently is it is the most abundant gas in the universe after hydrogen. Universe, 24% by weight hydrogen. That's kind of remarkable. Oops, I meant to say helium. 24% mass by weight of helium. On a smaller scale, it will make your voice squeaky. And again, on a larger scale, although not as big as the universe, it is very useful for cryogenics. Maybe not the cryogenics you're thinking of, more things like cooling superconductors in big research spaces or industrial spaces, but nonetheless, you can get it down to a really, really low temperature and it will cool things down. So how many moles of helium are there in 6.46 grams of helium? This is your job to solve, but I'll tell you right now, it looks like you're going from grams to moles. The solution is on the next page, so work this out and then you can flick forward to see if your answer is correct. So here we have it. One comment I'm going to make here is whatever problem you're solving, you need your strategy in place. Write down your given, figure out what you're solving for, get the appropriate conversion factor, set it up in a way so that your units cancel, and boom, you're there. You can also do a sort of a common sense check because the mass we're given here, 6.46 grams, is actually larger than the molar mass of helium, which is 4.003 grams. We would be very surprised, if not appalled, if our answer came out to be anything less than 1 mole of helium. Now the flip side, moles to grams. How many grams of zinc are there in 0.356 moles of zinc? Again, handle this one on your own, but note that in this case, you're going from moles to grams. So find your conversion factor, set it up, multiply out, make sure the units cancel, and again, boom, you have the answer. Ask yourself if it seems reasonable based on your quantities, and do this kind of common sense check that you see here. We are now going to tackle a multi-step conversion that brings together a lot of the steps that we have been studying so far. This may look a little bit intimidating at first, but actually you'll find if you break it down step by step, it's not nearly as bad as it looks. So the situation here is it's a hot summer day, but you have a wading pool that contains 50 liters of nice cool water. Before you take a dip to cool off, you decide that you want to calculate, as a chemist in training, exactly how many hydrogen atoms are contained in these 50 liters of water. So what do you need to do this? Well, what we've been using all along, conversion factors. The thing that may be a little puzzling at first is how to get from liters of water to grams of water. Fortunately, we have a way to do that. We can use two conversion factors. The first one is that there are 1,000 milliliters or 10 to the third milliliters in every liter of water. And a second conversion factor, which is that there is 1 gram of water in every 1 ml of water, which is the density of water. So if we take our 50 liters and we multiply 50 liters by ml over liter, and then multiply that by gram over milliliter, our units will cancel appropriately and we'll get how many grams of water we have in 50 liters of water. Then it's a fairly straightforward next step to convert those grams of water to moles of water using the molar mass of water. Now conversion 4 is something we haven't encountered yet, and that is how many moles of hydrogen are there in a mole of water molecules? Well, if you think about the structure of water, you can visualize that there are 2 hydrogen atoms bonded to an oxygen in every molecule of water. That's a 2-to-1 ratio. So the mole ratio holds up just the same for that. We have 2 moles of hydrogen in every mole of water. So that's going to be the way that we get from moles of water to moles of hydrogen. Quite simply, it's going to be twice as many. Finally, we need atoms. So we're going to take our conversion number 5, which is Avogadro's number, telling us how many atoms there are per mole of hydrogen. We're going to multiply by that, and that's going to be our last step. Now notice we can do this all in one step, as long as we make sure that everything is set up correctly and our units cancel appropriately. And we'll get an answer. 3 times 10 to the 28 hydrogen atoms. Needless to say, this is a huge number. This is more, for example, than 1 trillion trillions, but it's also real. This is the actual number of hydrogen atoms in 50 liters of water. Now, I highly recommend that you go through this problem step by step. You don't have to do it all in one step initially. It might be even a better idea to do each step individually and then follow with the second, third, fourth, and fifth steps. Then, as you become more expert, you will see that you can set this up in one step. So now we've established that there are 3 times 10 to the 28 hydrogen atoms, 50 liters of water. I don't know about you, but being able to calculate that makes me feel kind of powerful.